So welcome back. Hope you had a nice lunch or whatever. So it's my pleasure to introduce Mengchun Zhang from Imperial College, who today will be giving a talk on logarithmic Schrödinger equations in infinite dimensions. So whenever you're ready, Mengchun.
Yeah, thank you very much, Larry. Okay, so for today, I will talk about a very recent project joined with Larry Reed, the organizer, and also Professor Boguslav Zagniski. This project is about nonlinear Schrödinger equations. And for this talk, I will mostly focus on the general idea, the motivation background, instead of the technical details. Otherwise, things will be too messy. Okay, so the equation under study is this log Schrödinger equation, where lambda is a real number called coupling constant, and dx is the Becker measure in Rn. So this equation dates back to 1976, first introduced in the paper called Nonlinear Wave Mechanics. And since then, this equation has been intensively studied, and many applications have been discovered. For example, in quantum optics, quantum gravity, and information theory, because this log term corresponds to the entropy of the information. So as you can imagine, particular equation, for example, one can show that the mass, momentum, energy are conserved for this equation, just like the linear case. Also, one has solitary solutions, which are called Gaussians for these equations. Basically, this means you have a solution of a group of standing waves traveling along the space Rn. And also, if the potential V is smooth and at most quadratic, and if your initial condition F is sufficiently regular in this sense, then you have well-posedness for this equation. Actually, the third point is a very recent result, which is in a published paper last year. So with all these nice results, our aim is to extend this equation from finite dimensional space to infinite dimensional space. What I mean is that we are trying to establish the extension from Rn to Rs with any infinite set S. And obviously, this set S here is crucial because it somehow determines the structure of the physical space. For example, if S is Z, then you have a kind of a string of particles. And if you have a two-dimensional, higher dimensional lattice, you just have a kind of a plane or cube. But if S is a tree, things will be more tricky because the number of particles will grow exponentially with each layer. And if S is continuous, for example, R2, then you have some continuous field, for example, the Gaussian random field. In our case, we will mainly focus on these first two cases. Basically, we only consider regular finite dimensional lattice. So that's our focus. Hopefully, in the future, we can deal with more complicated cases like the other two. But for now, let's focus on these two, and we will carry on and then introduce some mathematical notions. But before we introduce the mathematics, one may ask that why we're doing this. Is there any physical significance of extend from finite dimensions to infinite dimensions? Well, the answer is yes, because if we consider Rn, then we're still in the microscopic system. This means if one wants to study large system, I mean large in the thermodynamic sense, then obviously one needs to pass the thermodynamic limit. And to do that, we need to extend from finite dimensional space to infinite dimensional space. And only then one can study macroscopic systems, which is a system that we can visualize. So yeah, the main flavor of this project is somehow to bridge the microscopic quantum mechanics and the macroscopic statistical mechanics. So that's the main goal of this project. Okay, now everything's good, but one can still argue that, well, why do we concern this log nonlinear reality but not other nonlinear reality? For example, in yesterday's talks, we have seen the polynomial nonlinearities. And the reason is because this log term admits a very special property called statistical independence. For example, given any two independent system, x1, x2, and consider the LSE on these independent systems with potential Vk and initial condition Fk. These are all independent. Then the product solves the LSE on the product space at x1 union x2 with the composite potential and the initial condition F1 F2. And well, I think we know that this is a well-known property for the linear Schrodinger equation. And actually, one can prove that if we have a nonlinearity in the form lambda times this function g and in the wave function, then in the first paper where this lower Schrodinger equation was introduced, they also actually proved that the above property holds if and only if GS takes this form. So either GS is linear or GS grows like this log term. So this means this log nonlinearity is pretty much the only choice that we have if we want to have this statistical independence property. Okay, now the question is, well, how can we use this property to extend from finite dimensions to infinite dimensions? Well, it's not hard because let's think for a simple example. Suppose this black box is the whole space, the infinite dimensional space Rs. And suppose your system can be decomposed or partitioned by finite independent systems. And for example, on each independent system, you have a wave function, initial condition, and then a potential. And then by the property I just showed, the product of all these wave functions will solve the log Schrodinger equations on the entire space with initial condition of the product and with the composite potential. So now you may wonder, well, now we already extended to infinite dimensions. What's next? Well, the question is, this idea has some holes. It doesn't work because first, the potential V, and second, the Lebesgue measure dx are both not well defined in infinite dimensions. For example, if you consider a uniform potential field, like the gravitational field or the magnetic field, then V1, V2, and V3, all these potentials will be uniform instead of decaying. Therefore, your wave will basically blow up in infinite dimensions. On the other hand, this Lebesgue measure dx in infinite dimensions is obviously not well defined. So basically, we have two problems: one for potential, one for Lebesgue measure. So how to solve this? Well, the idea is to use a ground state representation. Basically, we are using this representation to transform this equation into some other form, such that in that form, everything is well defined in infinite dimensions. So that's the idea. For the technical details, one can see that we use this transformation for any function u related to v by this differential equation. And then substituting this into this original equation, we have this new form with the linear operator L and the measure mu. So now, as you can see, this mu resembles the Gibbs measure. And this is good because Gibbs measure are well defined in infinite dimensions. So the problem of the measure is kind of solved. But one can still argue that, well, this guy can still blow up in infinite dimensions. Well, that's true. But I mean, if we consider the equation in weak form, what I mean is that if you consider the linear operator acting on test functions g, and you include everything in the measure mu, then everything should be well defined. Because, for example, if you consider g only depends on finitely many variables, basically g is a local function, and if u is a sum of finite range potentials, then these differential operators can only induce finitely many terms, right? So in this case, this LG is well defined, and then we're good to go. Everything should be fine. So as you can see, this is a rough idea of how we can make things well defined in infinite dimensions by using ground state representation. So now our focus will transfer from this equation to this equation here. So from now on, our focus will be this infinite dimensional LSE. in the weak form. And our aim is to prove the existence of solutions to this equation. Because, you know, if we prove the existence of solutions to this one, then we know that we can use this to describe microscopic systems. So that's the goal here. Okay.
Sorry, Mengchun, can I ask you a question?
Yes, please. Thank you.
How are you thinking about r to the power s? Is the set of functions from s to r, or is r times r times r like infinite times? Because
Yes,
then what is the Laplacian here? I don't understand.
Yes. I mean, thank you very much. Actually, I'm trying to sketch ideas here. I will properly, you know, define R to S just in a sec. Is that okay?
Yes, thank you. Sorry.
A few slides after this.
Thank you.
Yeah. So basically, your question will, basically your question will be asked in the first section, because we'll properly set up this infinite-dimensional computer space, and then the idea is to use kind of a sort of argument of finite dimensional approximation. Basically, we develop some estimates uniform in dimensions, but only works for finite dimensional SE. Then we use these uniform estimates to deduce the existence of solutions to infinite dimensional SE. So that's the idea. But as you mentioned before, first we need to properly define everything. So as I mentioned before, we only consider regular lattice, for example, ZD. So in this case, our space is R to Z to D. And well, I think the way to interpret this is that you can think this space as an infinite dimensional vector space. For example, all of the indices are in the lattice ZD. For example, if you have a Z2, then basically your particles are arranged in a kind of a two-dimensional lattice structure. And every particle will have a random variable in R. So that's the kind of setup. So yeah, I mean, for me, I would prefer just think this as an infinite dimensional vector space rather than function from Z to R, but that also works. Depends on your choice. So yeah, suppose we have this kind of a lattice structure for our physical space, for example, a crystal or something, and then we can introduce finite range potentials on this space. For example, consider a potential field given by a family Gx, where Gx is twice divisible and Gx vanishes if the diameter of X is too large. Basically, this condition here ensures that your potential is finite range. And well, the diameter basically means the longest distance between any 2 points in the set X. So as you can see that for a simple example, we can have this one where you have 4 different potentials covering the space. Well, obviously we have infinite dimensional space and infinite many Jx. And in this case, our potential u lambda is simply given by this form. Basically, if you have a non-empty intersection with x and lambda, then you add that Gx to your u lambda. For example, you can consider this example here, where lambda is this middle black square. And then in this case, your u lambda is Jx1 plus 2 and plus 3. And Gx4 is not in the sum because it's outside. So one thing to notice here is that although u lambda is supposed to be the potential energy inside lambda, it can still have dependence outside lambda. For example, this point, right? Due to the finite range. So this means that you would have some sort of boundary conditions outside lambda, which can still make things different for this potential energy inside lambda. So that's the setup. So given this potential, we can consider some kind of examples. For example, we can consider the bilinear case, where if x is j, you just have the quadratic case, and if it's jk, you have the bilinear case, and 0 otherwise. So in this case, your u lambda is basically this quadratic bilinear form, which could correspond to the harmonic quantum harmonic oscillator. Quite straightforward. So yeah, so given this space and potential, we can consider the local Gibbs measure, which is defined as this, basically a probability measure. The way to interpret this E lambda is to think that this is the kind of canonical probability distribution on the local system R lambda. The reason why E lambda takes this form is a matter in thermodynamic thermodynamic physics. So basically, we use some sort of a Shannon entropy minimization trick to deduce this form. But for this talk, we'll just assume that the canonical distribution inside R lambda is given by this form. Pretty straightforward. So now we have a well-defined local probability distribution. The idea is how to extend this one to global, to a global measure. And the idea is that we use this equation here. Basically, let mu be the global Gibbs measure on the whole space. And if mu satisfies this equation, then mu is a valid global distribution of the entire system. So that's the setup. And obviously, since this is an equation for mu, it could admit more than one solutions or no solutions. If there are more than one solutions, then it corresponds to phase transitions, because every global distribution corresponds to one phase. You have more, you have phase transitions. And if there is a zero solution, no solution for this one, then something goes wrong in your system. Then you may have to modify your potential U. And obviously, you may wonder that why can't we just have this limit here? Naturally, let mu be the limit as d lambda goes to infinity. Well, the reason is that this limit may not be well defined in some circumstances. For example, if your U grows faster than the bilinear case I just showed you, it's actually very hard to prove that this thing converges. Therefore, for this technical reason, we prefer to stick with this rather implicit definition of mu. You can find this in many literatures in thermodynamics physics. So yeah, so this is our overall configuration for the space. Now we will use this setup to properly define our logarithmic Schrödinger equation in infinite dimensions. And to do this, let's quickly recall that our equation takes this form, right? Because we only concentrate on the transformed equation, where mu is this Gibbs measure like measure, and L is this operator. And what we do is we substitute all these setups in here. So basically you have something like this. All right. So this time L is a kind of a global operator, where acts on every single site in the lattice, and UJ is simply the potential and J. And mu is a global Gibbs measure I just showed you before, which satisfies this DRR equation. But again, as I mentioned before, we need to consider everything in the weak form. So to be precise, we're considering this equation here. So this is our well-defined infinite dimensional log Schrödinger equation for this lattice setup. And oh, sorry, I need to mention that this test function G must depend on finitely many variables, otherwise things won't be well defined. And for simplicity, we'll just say G is a local function because it localized in some finite set. And our goal is to prove the existence of solutions to this equation here. So that's the main aim of this. Well, not the only one aim of the project, but the main aim for this talk. So the strategy to prove this existence is by, as I mentioned before, the finite dimensional approximations. So the first step will be to construct an increasing sequence which exhausts the whole lattice. Or you can think of a kind of an increasing sequence of cubes, something like that. And then for each of these finite volume, you construct a finite dimensional LSE denoted by this. And then from there, you have a solution phi n for this finite dimensional LSE lambda. And hopefully you can prove that this sequence of solutions converges in L2 mu. And then the limit defines a weak solution to the infinite dimensional LSE. So that's the whole idea of this proof. But obviously there's a problem here. And that is, how do we define LSE lambda for any finite lambda, for any finite volume lambda? This is important because obviously you have many definitions for how to define a potential inside lambda, and therefore you have many different definitions for this finite dimensional LSE. However, in our case, we will choose the most natural and the most probably the easiest option for this LC lambda, which I will show you just in a second. So to construct this LSE lambda, we consider this kind of a simplified setup where U lambda this time is defined by this summation, where X this time is strictly inside lambda. Well, just for comparison, this one is the previous setup where you have non-empty intersection, but now we have the strictly inside setup. So this means we won't have any boundary conditions outside lambda, which is much simpler. And in this case, the local distribution is simply given by this form, similar as before. I mean, as a comparison, I put these two guys here just for comparison and see how things are different. So now our focus will be on these, will be on this setup because they are simple and they correspond to the normal setup in Rn. Because I mean, normally in Rn we won't have any boundary condition outside Rn, right? So that's the reason why we are more interested in this setup rather than this one. Okay, so if we concentrate on this setup here, then our equation is simply given by this form, where the measure now is simply inside lambda. So we can just replace mu by this E lambda naught. And this operator now is again simply inside lambda. Oh, and again, this Laplacian and the gradient basically means the gradient Laplacian on R lambda. So that's the, for example, R lambda. Sorry, I'm using mouse to write, so it might be a bit strange, but yeah. So these gradient and Laplacians will be acting on the local space R lambda, just like in Rn, similar. So yeah, now we have this setup. What we want to do is that we want to use finite dimensional approximations of this system to approximate the solutions of the infinite dimensional SE, this guy here. And for any local, for any function in H1, sorry, for any initial condition f in H1 mu, which is localized in some finite volume. So that's the main goal. And remember that our section are structured like this, and we somehow already finished the first one. And we will begin the section 2, in which we will deduce some finite dimensional estimates for this guy here. Because as I mentioned before, we need to deduce uniform estimates for this finite dimensional LSE, so that we can use these estimates to approximate the solutions for this guy here. So now we're in the second section. So again, consider this finite dimensional LSE. And firstly, we have a very simple conservation law, mass conservation, energy conservation, where ENT is the entropy, corresponds to this nonlinear term. This is straightforward. The proof is not that hard, so we just skip. Secondly, we have some time-dependent bounds for the gradient and the entropy term. For example, again, for this equation, we have this gradient bound, depends on small lambda here. And also we have a bound for the entropy here, right? And the focus here, I mean, the important thing here is that all these bound and also the conservation law are actually independent of the volume of lambda. So no matter how large lambda is, you always have these two kind of different results, and the constant remains the same. And therefore, you can expect that we can use some sort of a compactness argument, because if you have an increasing sequence of solutions, which is increasing in volume, but for all these solutions, you always have the same estimates. Therefore, you can apply some compactness argument to deduce the kind of a weak convergence for your sequence. So that's the idea. But furthermore, we need one more estimate, which is called the finite speed propagation of information. So this means that if your potential satisfies some growth conditions, then you have this single site gradient bound. So this gradient J basically means the gradient and for the particle J, for the particle and J. So that's simply as that. And this Nj is kind of a distance between J and the initial region lambda f. Well, I need to say that this lambda f is the kind of the volume in which your initial condition f depends upon. So basically, you have this means that your initial dynamics are restricted in lambda f, and you try to compute the distance between any particle at J and at lambda f. And the result says that this kind of Dirichlet form will decay exponentially with this distance. So that's the idea for this theorem. And R is the finite range interaction. As I mentioned before, we need the finite range potentials for our setup. So yeah, this means that if you consider this Dirichlet form as some sort of energy, then this means your energy and the particle J, your energy of the particle J is decaying exponentially with the distance between J and the initial dynamics. And that's the whole idea of this theorem. So yeah, these are all the necessary estimates we will use to deduce the infinite dimensional existence. I mean, obviously, as standalone theorems, these are quite interesting to just play around. But now in this talk, we will just use them to deduce the infinite dimensional existence. So now we have all these nice estimates. We will begin to introduce our existence theorem. But for that theorem, we need some crucial conditions for which I included them here. So first, we need to assume the lattice is one-dimensional. Basically, your space is R to Z. I will mention later why this is the case. And second, we need the multi-spin interaction to be bounded. That is, if you have an interaction covering more than one particles, then this interaction has to be bounded and have bounded derivatives. So that's the case. Basically, the multi-particle interaction cannot grow to infinity. And for the third condition, we need a crucial functional inequality here, which is called log-Sobolev inequality. Basically, the measure E lambda satisfies this inequality, where C is uniform in F and lambda. I will explain how this inequality can help us. Well, I mean, at first glance, this inequality already helps us to bound the nonlinear term, right? Because recall that our nonlinear term is like this one, which is very similar to the entropy term. I mean, if you multiply the conjugate of phi lambda on the left-hand side, then you basically recovered this entropy term. Therefore, if E lambda satisfies this log-Sobolev inequality, then you can bound this nonlinear term by the gradient of phi. But we know that the gradient phi kind of satisfies some time-dependent bound. Therefore, you can bound the nonlinear reality. So this is why this inequality is important in this case. So let's first investigate what consequences we have if we have these three conditions. First, condition 1 plus 2 will imply that the density ratio of E lambda and E lambda circle is bounded above and below uniformly in lambda. Recall that E lambda is the local distribution with the boundary condition outside lambda, while E lambda circle is the distribution strictly inside lambda. And by 1 and 2, one can prove that the ratio of these the densities is bounded. And now I will explain why we need one-dimensional lattice. The reason is because, well, if you examine these two situations, let's first focus on the one-dimensional case. Then E lambda node, let the blue segment be lambda, and then E lambda circle is basically localized in this blue segment here, and E lambda is localized in lambda plus some range R boundary outside lambda. So this means these two guys only differ on the boundary with the range of R, and therefore you only need to concentrate on the boundary here. But I mean, if we have a one-dimensional lattice, then the number of particles in these boundaries are fixed, right? Independent of the volume lambda. If you just consider lambda as a kind of a light segment without any holes. Therefore, in one-dimensional case, this is nice. But if you consider the two-dimensional or high-dimensional case, then the range of boundary outside lambda will grow as lambda goes to invade the whole lattice. And therefore, this means your bound B here will somehow grow exponentially with the diameter of lambda, which is not good because it's very hard to control things in that way. Well, we believe that maybe you can introduce some necessary conditions on the potential so that you can also deal with high-dimensional case. But for this talk and for this project, we will keep things simple. Just consider one-dimensional lattice for now. Cool. So this is the first consequence. And how we can use it? Well, if we have this bounded density, then you can freely switch between one measure to another. What I mean is that, for example, you can consider E lambda F. Sorry about the writing. Suppose F is positive. And something like this. And vice versa. So basically, you can just change this measure with only a cost of constant in front, and that's good because all we need is this bound here actually. Because in later proof, we will try to switch this measure and this measure quite a lot of times, and therefore you needed this this kind of a condition to make things finite. Okay, so enough for the first consequence. For the second consequence. If you have 3 plus the consequence 4, then you can deduce that the distribution with the boundary condition also satisfies the log-Sobolev inequality uniformly in lambda. And why this is true? Well, this is kind of a well-known fact for log-Sobolev inequality, which says that this inequality is stable on the bounded perturbation. Because by condition 3, well, we already have an inequality for E lambda naught. And by consequence 4, we know that the density is the ratio of the density is bounded. Therefore, by this argument, we can conclude the log-Sobolev for E lambda. Very simple. And finally, we have by condition 2 and condition 5, the log-Sobolev for the global distribution mu. Recall that this mu is defined by the DR equation. So I mean, if by consequence 5 we have log-Sobolev for E lambda, then you can use some sort of a telescoping trick to deduce that mu also satisfies this log-Sobolev inequality. So that's the whole idea. Actually, this argument takes quite a lot of steps to prove, which is also one part of our project. But for this talk, we mainly concentrate on the PDE side. So let's just assume this is true. So now, with all these conditions and all these consequences from these conditions, we're now finally ready to introduce the existence theorem, which is that if we have the finite dimensional setup, LC lambda, as I introduced before, then we can use this one to deduce the existence of this infinite dimensional setup. And the theorem goes like this: suppose 1, 2, 3 holes, and suppose every local system admits at least one solution, because otherwise things won't make sense. And if these conditions hold, then there exists a weak solution or ultra weak solution to the LC infinity. So that's the main existence theorem. Obviously, I will not show the technical details to prove this because it's too tedious, but I will use the kind of the last 4 or 5 minutes to just show the general idea of how to do this. Let's come back to this example later. So the strategy is that, again, as I mentioned before, we construct a sequence increasing in volume, which will eventually exhaust the whole lattice Z. And let phi n be the solution on each finite volume lambda. And then our goal is to show that phi n converges strongly in L to mu. Then the limit of this sequence defines a weak solution to the infinite dimensional LC. And since we already have those finite dimensional estimates I showed you before, the gradient bounds, entropy bounds, mass energy conservation, and also the finite propagation speed, the finite speed propagation of information. And by all those finite dimensional estimates, we can show that phi n is weakly compact, and therefore it's weakly convergent. And because in Hilbert space, weakly convergence plus norm convergence equals strong convergence. Therefore, all the missing pieces here is this norm convergence here. So this means as long as we can prove this norm convergence, we can prove we can prove that phi n converges strongly in L2 mu. And from there, we will deduce the existence result. But how to do this? How to define, or sorry, how to prove the convergence of this limit? Well, the idea is to use the Cauchy sequence. Basically, if we can prove that this difference is controlled by some factor which decays exponentially in n, then we're good. Because by our construction, phi n is basically the one-dimensional cube. Therefore, this guy is equivalent to this condition here. And obviously, you can see this as n goes to infinity, this goes to 0, and it's summable. So therefore, you will have Cauchy sequence in the end. And then you can conclude that you have this limit here. So all the steps now point to this last step here. All we need to do is to prove that this difference satisfies this exponential decay. And to do this, we will make use of our log sublevel inequality I showed you before. Basically this. So recall that we assumed this log sublevel inequality as our condition 3. And by theorem, or actually quite a famous result for log sublevel inequality, this uniform log sublevel inequality implies a strong mixed condition, which is something like this one. And well, there's quite a lot of things going on, but all we need to focus is this exponential factor here. Because recall that all we need is this e to minus n here. So in this case, all we need is to use this factor here to deduce the sequence is Cauchy. And this E lambda Fg is basically the covariance between F and G. So what this tells us is that if we have this functional inequality, then the correlation in our system will decay exponentially with the distance. For example, if we consider the particle xi and xj, then the covariance decays exponentially like this. So that's the power of logarithmic log sublevel inequality. If we have this one, then we can deduce this exponential decay correlation. So that's why another reason why we need log sublevel inequality as a condition. And finally, by this exponential decay, we can prove that this difference is controlled by some exponential factor here. And the steps are as follows. So first, deduced by this mu n at this measure, and rho n again as this ratio between the densities. We use triangle inequality to deduce that this inequality here. And here we have f because we have mass conservation for E lambda naught, as I showed you before. So here actually we should have phi, but phi n, but by mass conservation we have f here. Again, this is a covariance here. So as you can see, this term is similar as this term. So all we need to do is estimate one of them. For example, let's estimate this guy here. And the trick is to introduce another factor, E gamma, and decompose this thing into two terms. And if we can choose a proper gamma, then one can use the strong mixed condition like this one to deduce that the covariance is bounded by this guy here. And as you can see, this is independent of lambda if we fix the initial condition f. And also you have this exponential decaying factor. So that's all we need. Just for a final remark, how do we choose the set gamma? So sorry, I need to mention that gamma is a finite volume sublattice in the lattice set. So basically gamma is a subset of the integer set. So to choose this gamma, we use something like this. So suppose lambda n is this red segment, and lambda f, the initial region where the initial condition depends upon, is this blue one. And then we can choose gamma to be concentrated on the boundary of lambda n. Because remember that lambda n is growing. It's centered at the lambda f, and it's growing to infinity. And therefore, the distance between gamma and lambda f will basically grow, and is proportionate to the diameter of lambda n. So that's the setup, the trick to introduce another term here, and then one can apply the strong mixed condition to deduce the Cauchy sequence. Finally, we can have a example of this existence theorem. So suppose we already proved this theorem by the idea I just showed you. Then we can consider a very simple example. Again, for any x, this means x is a finite subset of z, and consider this perturbed quadratic potential. This means if you have a single site, you consider quadratic potential. If you have multi-particle interaction, you consider Gx modeled by a bounded function Wx with bounded derivatives. Again, we need finite range interaction, so Wx has to be 0 if diameter x is greater than r. And suppose this Cj is kind of bounded above and below, then for sufficiently small strengths epsilon, the conditions in the above theorem is satisfied. This means if you have this perturbed quadratic potential, then you will have at least one solution to your infinite dimensional log Schrodinger equation. And then from there, you can use that equation to describe microscopic systems of some microscopic dynamics. So yeah, that's the main idea of this project. Sorry, with a bit of over 40 minutes. But this is the general idea. If you have more questions or comments, just let me know. So maybe we can discuss a little bit.
Okay, thank you. Thank you very much, Mengchun. So
Thank you.
Are there any questions? So, I mean, let me just ask something, we'll just point something out to begin with. So, Mengchun, you mentioned condition 3 for the uniform log Sobolev inequality. Are there any general conditions under which potential, the associated measure would satisfy that?
Yes. So, basically, since this E lambda naught is defined by your potential U, so you just need sufficient conditions on U in order this inequality to hold. And the one sufficient condition for condition 3 is that U lambda must be strongly convex at all sides in the lattice. So that's one sufficient condition by Bakery-Emery conditions. But obviously there are other equivalent, maybe there are other sufficient conditions, but for this one, we just concentrate on the strongly convex condition.
Okay, thank you.
Thank you.
Are there any other questions?
I have a question. Mengchun, how hard is to check the hypothesis of the theorem for your example? It's really hard, like, for example, to prove the log Sobolev inequality, or it's easy? What do you say?
I think if we have one-dimensional lattice and if we have bounded interactions, then this will be very easy to satisfy. Just as Larry asked, we just need the potential to be strongly convex at every size in the lattice. Then you immediately have this condition 3. So basically, yeah, because the idea is that because you have a strongly convex, condition on each side, then you have log Sobolev by some sort of the so-called Emery-Baker conditions. And because again your multi-particle interaction is bounded, you can use some sort of argument of bounded perturbation to deduce the log Sobolev inequality. So yeah, so for this setup only, it's quite easy to be satisfying. But for high-dimensional lattice and for unbounded multi-particle interactions, things will be tricky. We might need to work on that in the future. But that's a very good question. Thank you.
Yeah, and I have another question. So at the very beginning, you mentioned that the set S could be even R, like no discrete like set, but even R or Rn. So in that setting,
Yeah,
where is the candidate to be lambda, like to the finite volumes, like any submanifold could be, or you will try to
yeah, I
do
think
like
probably
some spheres or something?
Yeah, I think for this, actually, this case comes from a book of statistical mechanics. I think in that case, we don't have this discrete structure, and therefore you need to maybe concentrate on any finite volume lambda in R2. But obviously, as you mentioned, things could go wrong if we have continuous setup. So definitely we need some more machineries to deal with this case. I'm sorry that because actually all of our works are
Yeah.
dealing with, yeah.
No, you're right. There is no smoothness condition, so there should be no submanifolds. So it should be something else. You're right. Yeah. Sounds a bit complicated. Yeah.
Yeah.
Thank you very much.
Thank you.
Any more questions? Okay, in that case, thank you very much for a nice talk, Mengchun. And I guess we will start again we'll take a 10-minute break.